I welcome this webinar, which will focus on the new features and capabilities in GastroPlus version 8.6, along with a brief discussion of several new case studies focused on disease state PBPK modeling with the program. Vera Lukachova, who many of you know, is the team leader of simulation technologies and the GastroPlus product manager, and she will be the one presenting today. An opportunity to ask questions will follow Vera's presentation. You may either send your question using the questions pane on your control panel, or you may ask your question directly using the hand-raising icon. If you're using a telephone to listen to the call, please be sure to enter the unique audio PIN displayed when you join the call. When you enter your audio PIN, this enables us to unmute your line so that you can be heard. This webinar is being recorded for playback at our website, www.simulations-plus.com. It is now my pleasure to turn the presentation over to Vera. Vera?
Thank you, John. Hi, everyone. Good morning, good afternoon, whatever time zone you may be in. Today we will be focusing more on, of course, GastroPlus 8.6 new features, which I'm hoping some of you already started installing the new version released a few weeks ago. As you know, there were only a couple of major features, one on addition of built-in mini-pig physiologies and the population simulations in DDI module. These were two high-priority features that we identified based on the feedback from many of you having interest in these extended capabilities. We will look also at a couple of examples, just reminding you of how, even with the current capabilities of GastroPlus, you can customize the models and physiologies to account for some of the disease states, and we'll show examples for the liver cirrhosis and renal impairment as the two most frequently requested or discussed diseases. And at the end, we'll also do a brief introduction of what to expect in the version 9.0 and that we are trying to compile and finalize right now. So to start with new features in version 9.0 and specifically for the addition of mini-pig physiologies, you might be aware of a publication from Roche Group, Claudia Swenderhoff, publishing a summary of mini-pig physiological parameters back in 2013, which greatly helped us to implement this feature. And we've made some additional parameter refinements and filled in few additional gaps, mainly on the intestinal physiology based on additional literature sources. The default model that GastroPlus generates is representative of a 6-month-old male, 14.2 kilogram Göttingen mini-pig. Most of the parameters, especially the parameters on the PBPK physiology in terms of tissue sizes, blood flows, and so on, are really representative of Göttingen mini-pigs. But for the parameters where we were not able to get the direct information for this strain, we substituted from other mini-pigs. It would be mainly Yucatan mini-pig or different strains of pigs, whatever we were able to find and scale down to mini-pig physiology. The setup for the mini-pig physiology is very simple and straightforward, follows the nomenclature that you are used to for generating the physiologies or using physiologies for any other species. For PBPK, you will simply view or select mini-pig physiology from the species drop-down to create the default 6-month-old male mini-pig. And for intestinal physiologies, again, you will have two new physiological models, mini-pig in fasted and fed state for the intestinal physiologies. Brief validation, again, we've used the same models or the same data as used in the original publication for moxifloxacin and crizofulvin. Both IV and PO dose for each of these compounds. And as you can see, the default physiology is really nicely accounted for the distribution and clearance, so for the entire disposition of both dosage forms for both compounds. For the next highly requested feature for the extension of GastroPlus, the population simulations in DDI module. Just a brief introduction on what example you will see in the following slides, just to show the capabilities of setup as well as the results. I chose to do this using midazolam-rifampicin drug-drug interaction. Rifampicin is a 3A4 inducer, and again, there was a publication by Banig just a few months ago. I think it came out in February 2014, nicely describing the building of this model in GastroPlus, so that made our job much easier. And we paired that up with our midazolam model within the database of standard compounds that you've already seen and probably used in other drug-drug interactions. So going into the capabilities for the population simulations, we've tried to do this setup in a similar way as you are doing the population simulation setup in main GastroPlus. So make this feature as familiar to you as possible so you can readily start using it without the need for a special training. What you see here is the drug-drug interaction module form, where for my victim compound we have a midazolam, and for this specific case it was a case study where midazolam was administered as IV about 7 days after the rifampicin, and rifampicin was being administered for 6 days as a oral administration, and I believe it was 600 milligram dose. So rifampicin is a inducer of 3A4, so we have set up a induction constant as well as the Emax value. It is also metabolized by 3A4, so it would act also as a competitive inhibitor of 3A4. So we are accounting in the simulations, we are accounting for both effects, the competitive inhibition of 3A4 as well as the induction of the enzyme activity. And similar to what you are used to in main GastroPlus, just to bring that up, you know that in main GastroPlus, to set up the population simulation, all you need to do is on the simulation mode frame, just click on the population simulator. Right? It's exactly the same scenario, the same behavior in the DDI population simulations. You click on the population simulator setting, and which brings up the population simulator setup form, where you can set up, specify, and modify the CVs or variabilities on any of the physiological parameters, as well as the parameters for both compounds, or any of the compounds included within the model. So if you are running these drug-drug interactions with compounds where you've incorporated some metabolites, of course you would have option to select also the parameters for the metabolites. Additional parameter that may be of importance, especially for the DDI interactions, is the variability in victim administration time. Just to account for possibility of some of the subjects taking the victim drug maybe a few minutes earlier, or a few minutes or half an hour later than the average time. And depending on the strength and the type of interaction, this may have significant effect on when the interaction starts, and the magnitude of the interaction, and that would manifest itself in the average profile. So again, that's something that you can account for. The other aspect is you may be used to from running the population simulations in main gastro form to our recommendation for lowering or for adjusting the number of data points to be captured during the simulation to only the necessary number of data points to make sure that the simulations run as fast as possible. So to avoid or to make sure that you don't have to keep going back and forth for between the DDI form and GastroPlus form, you have now option to specify the number of data points directly on this form. So you can do all the setup on a single form. By clicking OK, you will go through a series of forms, especially when you have a PBPK model. Clicking OK will bring you to your familiar form for setting up your population in terms of age range, males or females, and so on. After the setup, once you set up the population simulation, the controls in the top part will change, and you will have an option now to specify how many subjects you want to include in the simulation, and maximum is the same as for a simple population simulations in In GastroPlus, 2,500 subjects. And you will see that you have here one button now for running a population simulation. If I scroll a little bit back, you know that for single simulations, for the dynamic simulations, to be able to estimate or get a prediction for the magnitude of the effect, you need to run two simulations. One is the baseline for running the simulation for each of these compounds as if they were administered with placebo, and the other one is running full simulation that actually accounts for the effect of these compounds on each other. With the population simulation, all of that has been lumped and is executed automatically. So when you click Run Population Simulation, the program will automatically run the baseline simulation as well as the full simulation for every virtual subject. So all you need to do is specify the sample size, and within single run, you will get the complete results on the variability between the subjects as well as the total effect based on the interaction between the two compounds. One thing to keep in mind is the simulation time. You do need to be patient with these. As you can imagine, for those of you who have run some single simulations in the DDI module, you know that these simulations generally run longer for several reasons. One is you are effectively executing at least two PBPK or compartmental PK simulations at the same time. That effectively prolongs the time for each simulation. To be able to see the effect, the program does need to run two simulations for each subject, one baseline, one full simulation. And the other aspect is the length of simulation, right? Most of the DDI studies are done with priming the subject with the perpetrator for several doses before the victim drug is administered. So the total simulation length is also increasing the time required to complete every single simulation. So that added up will add up to total simulation time for completing the trial. I did not put here a slide with the progress, but we did extend the label on that shows up over this table, which describes the progress of the simulation, and during the simulation you will get a complete output, complete progress. It will be showing you which subject it's running, whether it's running currently the full simulation or the baseline simulation for each subject, as well as the total progress of the simulation. So that should help you to gauge the total time, how much longer it's going to need to complete the entire trial. Once the simulation finishes, all the results will be displayed, all the mean results or average results will be displayed in the results window, just like you are used to from running a single simulation, the dynamic simulation. You get the outputs for the typical simulation outputs: fraction absorbed, fraction dose to portal vein, bioavailability, Cmax, Tmax, as well as AUCs. And you get these outputs for all compounds included in the simulation, victim compound, perpetrator, as well as any metabolites that might be included within the metabolic trees or within the models for any of these compounds. And you will get the output for DDI, for the baseline simulation, and the program automatically calculates the ratios as well. One thing to keep in mind is regardless of whether the interaction is an induction or an inhibition, the program calculates the ratio always as a result after simulation with perpetrator or with the full simulation divided by result of the baseline simulation. So that means for induction, if the induction is the prevalent effect, the ratios will actually be lower than 1. And the lower ratio means stronger interaction. So it's just something to get used to. Since we've run the population simulation here, we've done several different subjects. And in this case, I ran simulation with 15 subjects. So the results that we show here are just the averages for across those 15 subjects for all of these typical simulation outputs. But we have added an option to see the full output, the full statistics for all of these typical simulation outputs. If you click on this Show Stats button, a full form comes up where you can view the results for any compound included within this population simulation. And again, in this case, since I did not include any metabolites, it's only the results for the victim compound and the perpetrator. For each of the simulation outputs and for each of the runs, means full simulation, baseline simulation, as well as the ratios of these, of the full and baseline simulation, you will see the standard outputs that you are also used to seeing with the population simulations in In GastroPlus, and that's the mean simulated value, percent CV, minimum maximum value, geometric mean, as well as 90% confidence intervals calculated from raw data as well as on log transformed data. And to help you more easily identify the strength or the magnitude of the interaction, we've introduced the same type of color coding as you might have seen when you are running the steady-state predictions. Right? I didn't put here slides for the steady-state predictions, but for those of you who've tried some of those, you know that as soon as you get the prediction and the ratio of AUC, we do also color code the background of the cells from yellow to red, accounting for the strength of interaction. The same thing we are doing here for the ratios, color coding those, and to help you very quickly identify, am I looking at the weak or strong interaction. And the color coding is just as a reminder of what are the boundaries or what are the limits. If the ratio is within 25% of the baseline value, that's assumed to be no interaction and you will not see any highlighting for the ratios. Within 25%, it's actually if the ratio is less than 1.25 for inhibition or more than 0.8 for induction. Within twofold, it's marked yellow, as you would see for this interaction, meaning your averages would be between 1.25 and 2 if it's an inhibition, and would be between 0.5 and 0.8 if induction is the dominant effect. And similarly for interaction within 5-fold, this would be labeled in orange color, and finally showing red for very strong interactions if the ratio is more than 5-fold. And again, more than 5-fold would mean either the ratio is 5 and higher if the dominant effect is inhibition, or the ratio is less than 0.2 or up to 0.2 if the dominant effect is induction. Similar to the single simulations in DDI, of course, you can view the plot. And the plot, because it's a population simulation, is more similar to the plot that you would see with the single population simulations, with the population simulations ran in In GastroPlus. When you click on the Show Plot button, you would see the plot showing results for both baseline simulation, marked in pink, and the full simulation, or the simulation with the DDI effect marked in green. And the legend here reminds you which simulation belongs to the DDI, which one was the full simulation, which one was the baseline simulation. Since this was an induction, induction is the dominant effect, the DDI simulation or the full simulation comes up actually lower than the baseline simulation. You can view this plot for any of the compounds including in the model again. In this case, just the two parent compounds, midazolam and rifampicin. I only plotted midazolam since that's the really the true victim compound in this case, and rifampicin was not affected by the midazolam itself. But in some cases, you may have scenarios where the two co-administered compounds are more equal partners, and you may see effect on the PK of both compounds, and it would make more sense, or you may want to view both of the profiles. For the output file, just like with a simple population simulations that you would be running in main GastroPlus, the program automatically saves all the results and the progress in the output file as well, starting with the header reminding you what was the setup for population simulation, which databases you've used, which records you've used, which compound was marked as a victim, which compound was marked as a perpetrator. When you scroll down to the section with individual subject listing and results, these listing starts, of course, with the listing of parameter values for every parameter that varied in the simulation for every single subject. I sort of skipped those columns and moved straight to the end of those lines to show you the results. Now you would see the results for the typical outputs, FA, FDP, bioavailability, Cmax, Tmax, and AUCs for every compound included within the simulation. And for every compound, you will see the results listed for both baseline as well as the full simulation, with the full simulation marked as DDI. So for every single subject, for every single virtual subject, you see the listing of all the parameters that varied within the simulation, as well as the complete set of results from the baseline, as well as the full simulation. Scrolling a little bit further down, the CP time profiles, again, just like you would see with a standard population simulations, you do have an output of CP time profile for each virtual subject, for each compound of each virtual subject, and for each compound, both the full simulation marked as DDI as well as baseline simulation. And finally, at the end, you will have the summary statistics, the complete output of all the statistics for each compound. So the same thing that you can view on this form right after the simulation is finished, you do have saved for each of the compounds at the end of the output file. So all the information you can retrieve at any time. And this is just a comparison of the results running the rifampicin midazolam simulations or population simulations for IV dose. Those are the results that you were seeing so far, and those were marked or predicted more as a VIG interaction. I think we predicted just under twofold difference on the reported values depending on the dose, were somewhere in the range just under twofold to about 2.5-fold. For PO administration, you see the interaction is stronger. All our interaction terms or results are marked in red, suggesting strong interaction. The effect or the difference between the baseline simulation and the full simulation would be more than 5-fold, and you can see that this is heavily affected by the induction in the intestine, or by the induction of the intestinal 3A4. And again, just showing the plots that both profiles actually nicely represented the results or the clinical study results for IV as well as for this PO study. So that also serves as a validation of the rifampicin model that we are planning on adding to our DDI database of standards with version 9.0. So that was for the main features that we've incorporated within version 8.6. Again, the choice of these features was based mainly on your feedback and the requests that we were getting as a high priority request where we really need to include the additional expansions. And those were frequent requests for mini-peak physiologies and the extend the ability of DDI module to run the population simulations. Now, going to a topic which is not a new model or new features within GastroPlus 8.6, but it's really just a reminder of that you do have the capability of doing disease state modeling with GastroPlus. It does not include, GastroPlus right now does not include any built-in disease state physiology, so it's not a simple, one click or one checkbox type thing, do my simulation now as if this subject had a liver cirrhosis. It's not as simple and straightforward, but you know that you have the flexibility, you have access to all physiological parameters, which if you know how the physiology might be changing in given disease state, this flexibility does allow you to account for the disease states and do the predictions. And I'll show here just the brief examples of the two most frequently discussed impairments, and that's liver cirrhosis and renal impairment. When it comes to liver cirrhosis, I'm not going to spend too much time on the pathophysiology of the disease. As you know, it's a decreasing in liver function where the normal tissue is replaced with non-functional or scar tissue due to a variety of different conditions. Could be varying from alcoholism through bile duct disease, non-alcoholic diseases, and so on, viral diseases. So a lot of different causes that could result in changes in the liver function. And this could be limited to simple changes in liver function alone and could progress all the way to more systemic physiological changes, especially in the later stages of the disease. So depending on what degree of impairment you are trying to model, you may have to focus more on the liver itself, or will have to make changes in the entire physiology to properly account for these changes. And the good news here is that there actually have been already a couple of publications discussing or summarizing the major changes in different stages of liver cirrhosis, ranging from, of course, the functional liver volume, enzyme expression levels, but going also into more systemic changes like the protein amount in plasma, hematocrit, cardiac output, even glomerular filtration rate can get affected, especially at the later stages of the liver cirrhosis. So to incorporate these changes and to start making predictions for liver cirrhosis or for different stages of liver impairment, all you need to do is go down the table and make changes in the physiologies. Liver volume, I'm sure this is one of the easiest ones. If you know how much to change the liver volume, simply change the liver volume for your tissue in the physiology. Enzyme expression levels, again, this can be recalculated to the fraction and simply know by how much you need to change the expression levels from the healthy subjects. Blood chemistry in terms of how the protein amount is changing in the plasma, as well as hematocrit. And these two are actually have consequences also in the partitioning of the compound. And you can view how much the hematocrit and percent of protein in the plasma compared to healthy adults, how much that would affect parameters like blood-to-plasma ratio and plasma FUP. This is just an example as we were going from the normal subjects going down to subjects with, I believe this was, it's a mix actually, and should have been for liver cirrhosis C, or the highest degree of liver cirrhosis. So changing the hematocrit would actually increase the blood-to-plasma ratio. decreasing the plasma protein would increase the fraction unbound in plasma, and that would also affect the KP calculation. So you would want to recalculate your tissue plasma partition coefficients. Portal blood flow and hepatic arterial blood flow, again, adjusting changes in these tissues or adjusting the blood flows in these tissues. GFR, again, very simple change, simply adjusting the glomerular filtration rate in the kidney. For gut CYP3A4 changes, you have two options. We haven't seen any indications showing that the liver cirrhosis would be changing the functional 3A4 in a specific region of the intestine. So we would be decreasing the expression levels along the entire intestine by the same fraction. So you have an option to either overwrite all of these individual compartmental expression levels, or simply change or adjust your gut Vmax scale factor. As you know, this is multiplying the expression levels and multiplying the Vmax in your enzyme tables. So whether you change these values or simply set it as a scaling factor in here, that would have the same effect on the 3A4, and save it as a user-defined ACAD file. The most tricky part actually is adjusting the cardiac output, which is changing. It actually seems to be increasing in the liver cirrhosis. And the tricky part is that you would need to increase the blood flow in all of the tissues in this section down here to actually make up to the total cardiac output that you need or that was reported for the liver cirrhosis. So that part is a bit more involved, but again, it can be done by knowing how the physiology is changing. And as an example of how this works, we have a buspirone model, and I think I've seen on the list some of you who attended two of our latest DMPK advanced workshops. It's the same example that we've used during that workshop to work on the liver cirrhosis models. Buspirone is metabolized by mainly 3A4 enzymes into several different metabolites, and our scientist Joyce McWan, who worked on developing this model for buspirone, found a nice set of publications. The most extensive one was this one by Dawkins, showing the buspirone as well as two of its major metabolites after several different doses of the buspirone. So combining all of the in vivo data, in silico predictions for some properties, and in vitro parameters were available to create a complete model of buspirone accounting for buspirone as well as for these two metabolite PKs. And I'm showing here the simulations only for two of those doses. I picked the 7.5 and 20, so one of the lower, one of the higher doses. And you can see that she did a very nice job building a model accounting for the dose dependency of the buspirone. So what we've done from here, we've taken this model and used it to, or validated it, confirmed the performance of the model on another study which reported data for buspirone and one of those metabolites in healthy subjects as well as in subjects with liver cirrhosis. So for healthy subjects, we've simply taken all the parameters from this model, included default physiologies corresponding to the subjects included in this study, and verified that the model still holds. Now the next step was, again, using the same drug-dependent parameters, but adjusting physiologies exactly as I've described on these earlier slides. And again, if we have on the call some of those who attended our last two DMPK workshops, you know that that's exactly what we were doing, going step by step, changing all of those parameters exactly as I was describing, and making prediction for the liver cirrhosis. And you can see that the model, and based on the physiology changes, the model was able to predict that significant increase in the parent compound PK, and with very little change on this, at least this one metabolite PK, that was the metabolite that we had. So the match is not perfect, but it would show you a magnitude of the change that you could expect when dosing this compound in subjects with liver cirrhosis comparing with the subjects, with healthy subjects. Yeah. For the second frequently discussed or requested disease state is the renal impairment. And again, there may be variety of causes to renal impairment. And just like with liver cirrhosis, it can also have different degrees affecting different ranges or different parts of the physiology. The main causes would be the acute and chronic disease, and the failure may actually be at different parts of the physiology, and it would still be accounted as renal failure. Right? It could be a pre-renal effect where maybe the blood flow is affected, so it would be affecting everything downstream in the kidney. It could be directly in the kidneys, so it might be affecting only some of the functions of the kidney. Or it might be post-renal, more affecting just the urine flow. So it may not affect the distribution into the kidney, but it would affect the elimination of the drug from the kidney. And again, you would be looking at different stages, which would also affect how much modifications or where you need to do the modifications in the physiology to account for these renal impairments. And it could be anything from simple decrease in just the renal function in the first two stages, looking mainly at the GFR or renal function itself, all the way up to the later stages where, similar to the liver cirrhosis, you are looking not only at the renal function, but you may start seeing effects in the other physiological changes, the blood or plasma chemistry gets affected, and so on. And for that one, we'll go straight to the example that we have and the data that we have are again more on just the kidney function. So the example, we have amoxicillin, and you might have seen this example shown in at the AAPS a couple of years ago. Amoxicillin is a compound which is eliminated by renal secretion, mainly by glomerular filtration as well as active secretion. There is a number of transporters involved in the active secretion of the compound, but also in the distribution, reabsorption from the kidney tubules, and for oral doses also affecting the absorption of the compound from the intestine. And we did not have much of in vitro data. You are all aware of the current deficiencies in doing a direct extrapolation from in vitro to in vivo. And we also did not have significant amount of in vitro data for these transporters, but we did have a rich set of data in vivo conditions in healthy adult volunteers that we were able to use to build a baseline model. And again, this is just an example of some of the IV doses ranging from very low dose, 250 milligram, all the way up to 5 gram dose of amoxicillin administered by infusion. Some of these studies reported also cumulative amount of amoxicillin secreted in urine or excreted in urine. And we also had oral data, again, for a variety of doses ranging from low to very high dose with nonlinear dose exposure. So we did have plenty of data in healthy adults to calibrate the model to fit all of the necessary kinetic parameters for the transporters. Now, the next set of data came for the renal impairment. And as you know, a frequent endpoint, at least for the subjects, at least for the studies where renal function is assumed to be or is expected to have an effect on the PK of the compound, the creatinine clearance is, or creatinine concentration that can be turned into creatinine clearance and GFR, is frequently collected for individual subjects. And this was one of the study. I'm not showing the whole table, but at least part of the table where they did the study in different subjects with different degrees of renal impairment. And as such, they did measure the kidney function and the creatinine clearance. So I can do, taking the creatinine clearances for individual groups of subjects, we can turn these into estimates of GFR in each of these groups of subjects and simply adjusting the GFR from the healthy subjects into the excretion in the kidney or into the urine. This would account for passive excretion alone. Since for amoxicillin, we also have a significant portion of active secretion, and there wasn't much information for how transporters might be affected, we've made an assumption more that it would be an overall renal effect or overall renal impairment, and we made adjustments to the transporters and scaled the expression levels by the same proportion as we earlier scaled the GFR. And again, you might have seen this poster showing how well the program predicted, or the model predicted, on the PK for amoxicillin by just making these adjustments on the kidney function, accounting for the different groups of subjects. So again, it comes down to what do we know about the physiology, how much do we know the physiology, and especially those aspects of physiology that would be affecting the pharmacokinetics of your compound would be changing at different stages of the disease that you are trying to model. And through the flexibility that we are giving you within GastroPlus, you have an option to model all of these disease states as well. It is a little bit more involved. It requires you to do some changes to the physiologies, but it can be done, and you don't have to wait for us to actually make the change in the program. It is something that you can do immediately. Okay. So that would be for the second portion. And as the last part of today's presentation, we'll do a little teaser, remind you what you should be expecting in GastroPlus 9.0. And some of these you already know, so these would not be big surprises because we've been discussing some of these developments over the past couple of years. You know, we've been working on the dermal administration, and this is just a snapshot of our dermal model where we have a structure of the skin accounting for the major sublayers as the stratum corneum, as the top layer of the skin, viable epidermis, dermis, link from dermis to the systemic circulation, accounting for possible drug uptake and distribution through the sebum or hair themselves. A lot of focus has been placed on describing the effects in the vehicle, how the formulation might be affecting, accounting for the evaporation, and so on. Again, it has been discussed in a number of presentations, and we'll be happy, for those of you who are interested in the module, we'll be happy to do another demonstration. The next development, again, something that we've been working on for the last couple of years, was updating our oral cavity model, turning this into a more physiological model, again accounting for different regions in the oral cavity, how the absorption of the drug may differ from different regions of the oral cavity, accounting also for the saliva flow, accumulation in sublingual region, accounting for the swallowing process, how the swallowing is periodically removing the drug that might be in saliva, and how the dynamics of the drug partitioning into the oral mucosa and possibly coming back out in the saliva once due to the swallowing and replenishing of the fresh saliva may be affecting your drug absorption from the oral cavity. Next aspect, and this one may actually be the most popular with a lot of you, is introducing biologics module. And again, it's something that we've been working on quite extensively over the last year. And the first version would be incorporating the basic processes that every model for biologics should have, including simple distribution through the lymphatic flow, including the FcRn binding in the endosomal space and the protection of the antibody. Sorry, I should have said the first module will be focusing on the monoclonal antibodies. So FcRn binding of the antibody and the protection that it provides from the degradation of the antibody, as well as the processes of target-mediated disposition and target-mediated clearance. So the model will have the basic processes incorporated for the antibodies, and we are nearly finished that one. There are a couple of last changes that we are just finalizing right now. We are making some expansions on the capabilities of the ADMET predictor module incorporated within GastroPlus, and one of the frequent requests or suggestions that we kept getting for this module was allowing you to do a full model setup directly during the import structure. This, of course, becomes more relevant or more important, especially for the early discovery stages where you are trying to import a series of compounds and try to do maybe the screening. So you won't have to go, let's say you try to do prediction in human, you won't have to go into every single record after importing the structure and set up a PK model, set up physiology, possibly do your renal clearance and so on. You will be able to do all of this directly during the structure import when that first screen comes up, and the program will automatically set up that PK model, gut physiology, and possibly the renal clearance to all of the records in your database. And the next expansion that we are working on right now is linking this to the metabolism prediction. As you know, the recent versions of ADMET predictor released rebuilt and more accurate predictions on Km, Vmax values, and intrinsic clearances for at least CYP enzymes. So those are additional models that we'll be linking here to allow for the metabolism predictions, or for importing the clearance predictions. So through this simple structure import, you would have ability to do a complete model setup without having to go later on into every individual record to complete the model. We are working on adding new standard models to DDI database. One of them that I mentioned already is the rifampicin, which was the low-hanging fruit after the publication out of Roche, which was where the model was built in GastroPlus and was nicely described in the publication. We are still in the process of validation of our implementation. Of course, we need to make sure that they did the validation, everything was described, that the model does describe well on the PK or DDI with three or four substrates. But of course, we need to validate that we've implemented the model correctly, and that part is still in process. Another recently very frequent request for the new model in DDI is alternative 3A4 inhibitor. So we are working on adding the itraconazole model as a alternative to already existing ketoconazole model as a 3A4 inhibitor. So at least these two new models should be available with the GastroPlus 9.0 release. And the last aspect, which is maybe not a feature that anybody asked for, but hopefully it's going to streamline your administration of the GastroPlus. We are changing the licensing to the FlexNet Manager from Flexera software. It is a server-based license management system. For those of you who are licensing some of our chem informatics tools, ADMET Predictor, MedChem Studio, you know that those programs have already switched to this new licensing. And there is a lot of other softwares that are utilizing the same licensing. So the system, the server itself, is already placed in many companies, and for those companies the change would be as simple as just importing our license daemon. One of the big benefits is that it does not require exchanging the unlocking the codes over the phone. Everything can be done simply over email and importing the license file. So it should make the whole administration quite a bit simpler. It also is not relying on the computer ID. Some of you know and have a lot of problems with switching computer IDs when plugging the computer to different networks and things like that. So that should not be a problem anymore with this new licensing system. At the conclusion of the presentation, just because I did the presentation, it doesn't mean that I'm doing all the development. We have a very nice group of smart scientists behind the development of our programs. The GastroPlus is mainly developed by the simulation technologies team. Jim, Hai, Kay, and Jessica all are doing very nice job on helping on the development of GastroPlus and the other softwares. But of course, we do get a lot of support from the other teams at the company, computational technology, cheminformatics teams, consulting studies teams, and so on. So we need to give the credit where the credit's due. And that concludes the presentation, and I think we'd be ready for any question that you may have on anything that we've discussed here or other questions on the GastroPlus.
Thank you so much, Vera, for a really excellent, insightful discussion and presentation. Once again, if you'd like to ask a question using your telephone, please use the hand-raising icon on your control panel and be sure to enter your unique audio PIN. I do see that there are a number of questions that have come in written, and so we'll go to those first. I do want to mention just one additional thing since we ended with the discussion on new licensing. Another thing that we have been testing and now have available in terms of accessing GastroPlus is a cloud-based offering of the program. So we have had a number of teleconferences with several large pharma groups and their IT departments talking about what is available. If there is anyone who is interested in learning more about what we can do through the cloud, please feel free to reach out to me. You should have my contact details, or just go and contact us directly through the website. So we'll get to the questions in the order in which they were received. Vera, the first one is, just wanted to check regarding the population DDI simulator. Can you add some % CV on clearance to cover the population variability?
You hear me?
There you go. Yeah, now I can. Yeah.
Okay. Yes, you do have. I'm not sure what happened. I wasn't even muted, but okay. So you do have the same offering of the parameters as you have with the simple simulation, but you have this offering with all the compounds that are included in the DDI simulation. So you would have by default any non-zero parameter value is selected as a possible variable parameter, and I think I opened this just from a demo database, so I would have liver clearance somewhere here, and you can change, so we come with some defaults, but you can change the CVs on the clearance as well. And the same applies for your DDI population setup.
Okay, thank you, Vera. Another question is, can you convert your observed clearance in man to a CLINT specific to a SIP if you know that the victim is, for example, 100% a 3A substrate?
Okay, so you have your observed clearance in man and you want to, okay, to the SIP specifically. Actually within the PBPK model, that is kind of done automatically. Let me open a, doesn't matter which one I'll take here. So you know that if you enter a clearance into the liver, let's say, the program automatically does the conversion into the intrinsic clearance. And if you know that the compound is metabolized 100% by a single enzyme, this would be representing the intrinsic clearance of your specific enzyme. The only word of caution that I would mention is that this conversion is really accurate for if you are dealing with just a simple perfusion or flow-limited tissues. There are some additional assumptions that would come to play if you are working with permeability-limited tissues, so that would get more complex. But for the simpler tissues, this conversion is done automatically.
Thank you, Vera. Another question, two parts. The first is, does 90% confidence interval of the log transformation with the population simulations go with the geometric mean ratio?
Yes, that would be correct. So within the results, you have the 90% confidence intervals would go around the simple arithmetic mean. The ln transformed 90% confidence intervals would go with the geometric mean.
Thank you, Vera. Second part, in your estimation, how long does it take to run a 15-subject population simulation with DVI?
Well, that really depends on the type of, on how long you try to run the simulation, the type of interaction. Generally, it would be longer when you are dealing with a time-dependent inhibition or an induction, as I was doing here, than if you are dealing with just a simple competitive inhibition, because competitive inhibition does not have to account for the changing activity of the enzyme and so on. For example, for these simulations, I didn't time it. As I recall, I think it took about half an hour or maybe longer to complete those. No, I think this was longer. I think this was close to an hour to complete these 15 subjects. But I've done a number of simulations in the past with a simple competitive inhibition of ketoconazole and midazolam, and those were quite a bit faster. So it really depends on number of factors, and the type of interactions does play a significant role in that time as well.
Thank you, Vera. Another question. This is about adjusting the blood volumes for the other organs to correct for the cardiac output when you're modeling a disease state like liver cirrhosis. Can you not simply click on the balance button found on the pair physiology window to balance cardiac perfusion rates across all tissues?
The balancing is not really, so just for those of you who may not be familiar with that feature, we do have the balance model in here. You could do that as a by changing the cardiac output in here, and that would balance automatically. That would actually automatically balance and decrease all of the corresponding tissues. The only tricky factor there is that the liver and perfusion is affected by other factors. So in that part, you actually want to account for, let me see, where can I find that table? You want to account for the liver blood flow affected by portal flow as well as the hepatic arterial flow, which may not go exactly in the same ratio as the cardiac output. But as a simplest option, that would be one option to look into.
Thank you, Vera. This is now related to the dermal model coming in version 9. Is the dermal dosing compartment separate from the general skin compartment? In other words, will PBPK predict the concentration in remote skin?
In part, yes. So the and that's the part that we still need to finalize, is to make sure that the administration compartment is generally going to be, or in most cases, going to be only a small portion of the skin. The rest of the skin would be receiving the drug from the systemic circulation. So you would be able to do a prediction as to how much the drug is getting into the rest of the skin, but we don't have this capability, as you see, that's disabled here, to specifically say or measure a concentration in the specific portion of the skin. Let's say at least in this first version, we are not doing the capability where you could specify I'm dosing my drug on face, and I want to see how it's going to be appearing on the left arm or something like that. The sampling region would be a skin compartment in general.
Thank you, Vera. This question seems to also be related to the topic. Could one define an effect compartment, such as a joint, below the dosing site?
Not really, as that kind of joints. We don't have that capability right now. We'd have to think about what kind of workaround or what kind of extension that would require for a specific compartment. These individual compartments, I don't think we've done or planned for that at the moment to link these into our PD model. in time, we'll definitely do the links from these individual skin compartments also to our PD models. But up until now, we have not considered that type of distribution going into a specific joints or similar compartments.
Okay, thank you, Vera. Another question, is there any way of modeling pediatrics in the current version or in any upcoming versions?
Of course, you've had the pediatrics for years. For several years, you had an option to model pediatrics from 1 year old. In the last release with version 8.5, we've extended this capability to model also infants and being able to go as low as 16 weeks premature newborn. So you definitely have the capability of doing the pediatrics. And we've also had a number of posters, presentations showing the predictions in the pediatrics. Also, some of the publications from some of our users were dealing with the predictions in pediatric subjects.
Thank you, Vera. Still related to this topic about populations, can you do simulations, population simulations in DDI for certain groups, for example, Japanese versus Caucasian?
Yes, with the DDI module, actually let me open the DDI and walk you through the setup. I forgot to put in that kind of setting or the slide showing that setup. But if we stick with the Buspiron model here and try to do interaction, let's say ketoconazole, if I want to do the dynamic and I go to population, once I set up my parameters and in the next step, okay, you do have an option. With the default physiologies, you would have an option to set up the physiology. I'm sorry, I forgot. We've got that limitation on the physiologies is still unfortunately there. So in a population simulation, you would have an option to select the age range as well as select the population, either American or Japanese. And within each population, you have an option to specify the male to female ratio. The one thing you cannot do right now is to have a mix of a mixed population, let's say specify on certain % of American and certain % of Japanese, but you can do a population or the population simulation in each of these.
Thank you, Vera. Another question, besides liver cirrhosis and renal impairment, have there been any other disease state models which have been explored and in which you could share some references?
I'd have to go back in my files because this has been a few years ago, but I do believe I looked at some simulations in heart condition. I think I had some data for congestive heart failure and changing the cardiac output, and one might have been obesity as well, but I'd have to go back. It's been a few years ago since I explored those.
Thank you.
So if you, I'm not sure who posted that question, but if you wanted to send us an email, I'm sure I can find that presentation and send that presentation and the comments on that.
Perfect, thank you. Another question is, for the population simulator, has there been an increase in the total number of output data points that can be saved? For example, long DDI runs with large population size.
No, the limitation, well, we've increased the limitation a little bit. I think we've doubled it. I'd have to go back, I can remember. But it was increased a little bit, but not very significantly. So it would still be a fairly limited set of data points to be saved, especially if you have a lot of subjects. So in that case, you may need to run a few smaller trials rather than one big trial.
Thank you, Viera. There is a question regarding the DDI predictions, and this is just some general guidelines. Is there anything that could be done with to explain any uncertainty that might be seen with in vitro values as inputs into the model?
Well, the population simulation does include the variability on the parameters as well. On all the parameters, you can include that variability. So within the metabolism, you would have ability to include the variability on K and Vmax values, as well as Ki or other interaction, depending on what type of interaction it is. So through this, you would be able to account for that kind of variability. And you do have a complete control over which parameters you want to look into. So if you want to do just a prediction of how variability in my, or uncertainty in my in vitro values, let's say K and Vmax, Ki values, is affecting my predictions, you can simply select only those parameters. So you can go to the variability only in K and Vmax, Ki, or if I had induction, my EC50s, and look at the variability of only those, or uncertainty of those.
Thank you, Viera. I do see one person with their hand raised, so what I'll do is unmute the line and see if they want to ask a question over the phone. Hello, Fagan. Are you there?
Yes. Hi, John. I know.
Hi.
I'm the only one raised the hand. We had a question regarding the version. We have GastroPlus 8.5 versus 8.6. I know in the email, in previous email, you talk about fix some bugs. I don't know what kind of bugs you mentioned. Is there any big impact for us to do something, or it's okay, we don't update right now?
To be honest, this has been a long process, and I know we fixed number of bugs. I don't think there was anything very critical because we would definitely be alerting you of those. But if you want to send me a reminder email, I can send you a list of bugs that were fixed, and you can then make a better assessment of how much that would be affecting your simulations and whether you need the update or not.
Okay, thanks. The second question regarding the demo version release. I know, John, basically you said it's the fourth quarter of 2014. So still on the target 2014 or not?
As of today, we are still on target by the end of the year. As you know, things change very quickly, and depending on what may come our way within next 2 months, we are really trying hard not to slip into the 2015. We are really trying to get it done before the end of this year, and as of today, we are still on the target.
Okay. All right. We'll catch you guys later. Thanks.
Okay. Thank you, Fagan. Yeah, just to follow up on Viera's comment, some of you may be disappointed to know that you won't be seeing as much of Viera in the fall, because it is one of the goals of the marketing and sales group to try and keep her in the office as much as we can over the next couple months to make sure that that version gets out in 2014. It seems like that has finished the question-answer session. I don't see any other questions coming in through the chat log, nor do I see any other hands raised. One last thing that I would like to do before we officially end today's discussion is just make sure that everybody is aware of some new developments that we've had here at Simulations Plus. So we did have an announcement come out within the last couple of weeks regarding our recent merger with Cognigen. And for those of you who don't know too much about Cognigen, they are one of the leading consulting groups that provide services related to pharmacometric analysis, model-based drug development strategies, PK/PD modeling support, due diligence, and a host of other things. And we're really, really excited because this fits in nicely with the modeling and simulation tools and technology and also consulting services that we have been providing over the years. And so now, literally from the point at which you begin sketching chemical structures and designing compound libraries all the way through to regulatory filings, Simulations Plus and Cognigen consulting groups can utilize our combined modeling and simulation technology and expertise to help you make better project decisions sooner. And I encourage you to learn more about some of these combined offerings that we have by visiting us at an upcoming show. We're going to be at the ACCP annual meeting that's taking place September 13th through 16th in Atlanta, and we're going to be in booth 302. We'll also, of course, be at ACOP October 12th through 15th in Las Vegas, and as soon as the formal booth assignment has been made, we'll be sure to pass it along. And then we'll have a very big presence at the AAPS annual meeting November 2nd through 6th in San Diego. We'll be in booth number 1642. If you don't have an opportunity to go to any of these conferences, of course, you can always go to our websites, which you see listed here at the bottom of the screen, or feel free to contact myself, Viera, anyone else on staff directly. So that concludes today's webinar. If you missed any part of today's presentation, the playback will be available again at our website, www.simulations-plus.com. Thank you so much for all the time and for joining us, and we hope you have a wonderful day. Take care.